Today's lesson is going to be graphing exponential functions. And we're going to start off with the simplest, or one of the simplest, exponential functions, a to the x power. Now, in order for these properties that we're talking about for the graphs to remain true, a has to be greater than 0, and a cannot equal 1. Okay, if a is negative, what happens is we end up getting a mishmash of discrete points and places where it's undefined, because raising a negative number to exponents gets messy. So for this to be a smooth, clean curve with predictable properties, we need it to be greater than 0. And also it can't equal 1, because 1 to anything is just 1, so it becomes a very uninteresting graph. All right, so this set of restrictions are true for all the graphs of the exponentials we're going to be talking about. Now, specific to the first example, if a is bigger than 1, what will happen is you're going to get your basic exponential growth graph, which is going to look like this. It's going to have a domain of all real numbers. It's going to have a horizontal asymptote at y is equal to 0. And the domain is going to be everything above where that asymptote is. Right now, if a is less than 1, and it's also assumed that it's going to be greater than 0 because of this, that's going to be your basic exponential decay graph. It's going to look like this. It's still going to have a domain of all real numbers. It's still going to have a range of everything above the horizontal asymptote. That horizontal asymptote will be at y is equal to 0. Okay, other common variations that happen, if we take that exponent and give it a negative coefficient, but keep that a greater than 0, greater than 1, not greater than 0, that will cause the graph to be decay instead of growth. And then the last situation we're going to talk about, okay, what if we give that a negative exponent and that a value is between 0 and 1? Okay, it's kind of like the two things that cancel out to cause it to be the two things that cause it to be a decay cancel each other out. So if that's greater than 1 and positive, it's growth. If you make that less than 1, or you make that negative exponent, it'll cause it to be decay. If you do both of those things, meaning this thing becomes less than 1 and that's negative, that brings it back to growth. All right, so those are the basic facts that we want to be aware of when we start graphing our exponentials. And then the other thing we're going to be mixing in are basic rules for function transformations. If you add or subtract up in the exponent with x, that's going to slide it left or right in the opposite direction of the sign. If you add or subtract out here, after the exponent part is done, that'll move it up or down in the same direction as your sign. If you put a coefficient in front, that'll cause a vertical stretching or a vertical compression of the graph. And if that happens to be a negative in front, that'll flip the graph down. So what we're going to do is look at a couple typical types of examples that you're responsible for in this class in terms of the level of difficulty and the types of things you'd be asked to figure out as far as the graph goes. So we're going to do two examples. Let's zoom in a little bit here. We're going to neatly sketch the graph. We're going to identify the domain, range, its intercepts, and its asymptotes. All right. First thing I want to do is get a rough idea before we do anything specific of what this graph is going to look like. All right. This base here is bigger than 1. 8/5 is 1 3/5 with a positive coefficient in a variable. which is in the exponent. So what we have here is this is a basic exponential growth graph like that. That plus 1 is going to shift it 1 to the left. And that plus 2 is then going to take it and shift it up 2. So after we take this and shift it left 1 and up 2, it's in this general neighborhood like that. So we just have a rough idea of what to expect when we get this in our calculator. Now, as far as identifying the key features, our exponential functions have a domain of all real numbers, and we're going to be expressing this in interval notation. They all start with a horizontal asymptote at y is equal to 0. That'll move up and down with any vertical shifts. So it's going to go up 2. So we have a horizontal asymptote at y is equal to 2. Okay, the entire graph is either going to be above or below that asymptote. Unless there's a negative sign to flip it down, we know it's going to be above. So it's going to be from 2 to infinity. Now, as far as the intercepts go, if this shifted up like that, this graph will never cross the x-intercept. It's not going to have one. Okay, it will have a y-intercept, and we're going to get to that in a moment. Now, some of these graphs, when you sketch them, they may look pretty steep, and it may appear as though perhaps there's a vertical asymptote, but none of these exponentials will have one. So if they never have one, it begs the question of, well, why is it here? Well, one of the things we're going to get to, I don't know, next lesson or a couple away, I'm not sure where it falls in the sequence, is we're going to be graphing the logarithmic graphs. With logarithmic graphs, these two guys trade places. They'll always have a vertical, but never have a horizontal. So ultimately, when we get through the first half of the chapter, when the logs and exponents are mixed on the same page at the same time, you have to be able to sort out which one has which type of asymptote and which one doesn't have. All right, so as far as what we know we can fill in on the graph real quick, based on what we've done so far, the only thing we know for sure is it has a horizontal asymptote at y is equal to 2, and we know the basic shape of roughly where it's located. So now we're going to go to the calculator to help us out with the rest of this. So y equals, clear out that old equation, and it's going to be 8 divided by 5, raised to the x plus 1 power, and then plus 2. And for now, where we are in the chapter, I pre-chose examples and problems so it should fit nicely in the standard zoom window, which is a zoom 6. And we get pretty much what we expected in terms of the rough shape and location. But as far as filling in our features over here, the only thing we have left to find is the y-intercept. Okay, the most efficient way to find a y-intercept on a graphing calculator is if you hit trace. The calculator typically is going to default to starting to trace at x is equal to 0. Well, y-intercept is when x is 0. So it traced right to the point we want. 0, 3.6. Okay, very often these numbers can be rather messy decimals. This was a nice clean 3.6, but follow rounding instructions if there are any associated with the problem. All right, so 1, 2, 3, 3.6 is roughly there. What I'm going to do is go to my table and get a couple points that are useful here. So going on the negative side, negative 1, 3 is a point. Negative 2, 2.6, and we really don't have to go any further than that because we know it's going to approach this asymptotically. So the decimals that we get from the calculator are going to be things that are too precise to graph anyway. What we need is a couple points over here. So 1, 4.56. That's roughly here. 2, a little bit past 6. And then the last one we're going to fit is at 3 and about 8.5. Count that right? 1, 2, 3, 4, 5, 6, 7, 8, 8. So that's more than enough information to get a pretty accurate graph, it's going to look like that. All right, next example. Our function here is f of x is equal to 1/2 e to the negative x minus 5. So what I want to do is the same thing I did to start off the last one. I want a rough idea of what I'm expecting here. Well, e is about 2.7. So the important thing is that base is greater than 1. So we have a base greater than 1. And we have a negative coefficient in our exponent. So that means that we are looking at the parent function here to be your basic exponential decay. Now, as far as what the rest of the stuff is going to do to it, we don't have anything added or subtracted with the x, so we don't have any left-right shifts we have to consider. That minus 5 is going to bump the whole graph down, and then 1/2 is going to vertically compress the graph like this. So it'll be flatter instead of steeper. So we know that we're going to have a horizontal asymptote down here at negative 5. It's still going to have that basic shape, but be a little bit flatter. So it's looking like roughly like that. So we're expecting both an x and a y-intercept for this particular graph, as opposed to the one we did above it. We had a y but no x. All right, so as far as filling in this stuff, all of our exponentials have a domain of all real numbers. We know we have that horizontal asymptote at y is equal to negative 5. We know the entire graph is going to be above that negative 5. Now, just as a reminder, say that half in front was negative, that would cause it to flip down and we'd be below the horizontal asymptote. Okay, typically, for what we're doing now, that tends not to happen. It's much more common to have it above. Okay, x and y intercepts, we still need a little bit more time or a little bit more work to figure those out. And none of these have the vertical asymptote. Now, I mentioned in the previous example that the exponentials have a horizontal but not a vertical, and then that's going to flip when we do logs. Okay, the other thing that's going to flip is this here. Once we start graphing our log functions, what will happen is there'll be some kind of restriction in the domain, and the range will be all real numbers. So again, for this particular worksheet on this particular lesson, it may seem silly. Why are they always asking us for the domain? It was always all real numbers. Once this mixed in with logs, that's not true anymore. Okay, as far as sketching, 1, 2, 3, 4, 5. So we know we have our horizontal asymptote down here. Let's get this in the calculator. Go back to y equals, clear out that equation. I'm going to put it in as 0.5, a little bit cleaner. And then e to the x is the second function above ln. Negative x for the exponent, minus 5. And we're still in that standard zoom window, which everything will fit nicely for now. So roughly the location and the shape that we were expecting. So things seem to be pretty good. We can get the y-intercept by hitting trace, and typically the calculator will default to starting at x is equal to 0. So 0, negative 4.5 is our y-intercept. If you didn't get a clean decimal, make sure you follow the round-off instructions. And then for x-intercept, what we're going to have to do is second above trace is the calc, and then the 0 function will allow us to find x-intercepts. It's going to ask us those 3 questions, left bound, right bound, gas. We've been here before in terms of knowing how to handle that. And 2 decimal places, that'll be negative 2.30. Alright, so we can plot those 2 points. X-intercept negative 2.3, so that's about there. Y-intercept negative 4.5. That's about there. And we'll go to the table and grab a couple more points to flesh out the curve. Alright, we don't need anything over here. We know it's going to be approaching that asymptote. Negative 1 would be a good number to know. So about negative 3.6. And we'll get a point or two up in this neighborhood. So 1, 2, so at like negative 3. We are at a little over 5. And it looks like we're not going to fit anything else because we jump up to 22. So as far as meaningful points, that's the best we're going to be able to do. Draw in our smooth curve, show it approaching the asymptote, put the arrows on each end. That'll be good. And I'm not sure if we are going to have any paper pencil quizzes and tests with this. We've been pretty much on Edulastic for a while now. But if this does turn out to be an assessment that we take in class with paper pencil, what I look for when I grade these is the asymptote shown. Is it in the correct spot? Are the intercepts accurately shown? Do you have at least 2 or 3 other points, depending on the nature of where the curve is, to be reasonably accurate? Draw a smooth curve that connects them, arrows on each end. That's what I'm looking for. As far as some details over here for domain and range, I expect those to be in interval notation. Okay, x-intercepts, y-intercepts should be in point form. If you have an asymptote, make sure you're specific as opposed to whether it's an x or a y. And don't leave things blank. If there is no vertical asymptote, make sure you write none. Leaving it blank is I forgot it. Leaving it blank is I'm not sure, Mr. Haggard. All right. Next thing I want to address. We found the x and y intercepts by using the technology. X and y intercepts can be found sometimes without the technology. Okay, as a reminder, no matter what you're ever graphing, your entire math life, you can always find x-intercepts by letting y be 0, y-intercepts by letting x be 0. So one way to find the x-intercept, for this as an example, would plug in 0 for y. And then solve that equation for x. Now where we are in the class right now, technically we haven't learned anything about using logarithms to solve equations. You may remember from Algebra 2, that's a topic we're going to be getting to soon. But based on where we are specifically by what we were taught in this class, we don't have the ability to find that x-intercept right now. After another lesson or two, I forget the sequence of where it falls, then finding that x-intercept with logarithms will be an option. Okay, the y-intercept is when x is 0. Okay, this one we can easily find without using any logarithms. Anything to the 0 power is 1. 1 half times 1 is a half. A half minus 5 is negative 4.5. So we really didn't need technology to be able to identify that. That one's pretty easily done with a little bit of mental math. All right, that wraps it up for today's lesson as far as what we need to know right now about graphing exponentials.